Now, in that case, the difference was negligible because of the total size of the system. But you might run into an application where that non-structural mass should be carried on some appropriate axis. Finally, you can have taper of the beam, and some elements, such as the MSC Nastran beam element, will allow sections along the beam to have different cross-sectional properties, and then those can be read in the data set. The end release concept is also very important for beams, and this applies to all types of beams. What you might have is a pin joint or some kind of a slot at the end of a beam which will relieve the moment or shear forces present there. I've drawn two examples at the two ends of this beam, and presumably the beam is long and slender, and I've not drawn the intermediate portion, such that these end fixtures are only a very small part of the total beam structure. I've drawn a curious fixture at the left end in which certainly the pin acts to relieve the moment about the y-axis. If I create a system of coordinates here, x, y, and z. And the cards that describe this beam are often set up with a end release field. Here's the end release field for the left end. Here's the end release field for the right end. Now, rotation about the y-axis would be the 5 coordinate. Then there could be also a differential rotation about the z-axis here, just by the different ends of this pin sliding in the slot, and that would release degree of freedom 6. Then there's certainly translation along the x direction, which is degree of freedom 1. And then lastly, because the joint is kind of sloppy, it could translate in the y direction, degree of freedom 2. And so the only restrained degrees of freedom then are the vertical displacement, which is z, which is 3, and then rotation about the x-axis, which is 4. At the right end, we have a little different situation where the release allows x translation, which I show here, and then also releases rotation about the x-axis, degree of freedom 4. The simple theory that we've discussed, which is the Euler-Bernoulli theory, is very good for compact cross-sections. But when you go to thin-walled beams, then you can have some analysis problems. One reason is that the cross-section itself can change shape. It can warp and go out of plane, and then within the plane it can deform greatly. This is worse for the open-walled sections than the closed. I'll refer you to classical textbooks on this. Typical courses that are given around the senior level in mechanical engineering, civil, and aerospace departments often will have considerations of thin-walled beams. I can give an example for the problems you get in the closed sections. I used to test the thin-walled beams used in vehicles, automotive primarily, and I bent these beams about an axis shown here, and then I twisted them as shown here. Nature is perverse in the sense that these thin-wall beams, as they're loaded, will tend to cripple at a cross-sectional location. And what happens is that the walls of the body will move toward the neutral axis in a way to minimize the moment of inertia. So it's sort of a self-destructive behavior. And this particular cross-section shown here will become even more extreme until the body actually does fold at that point. That can be triggered elastically, but ultimately progresses to a complete plastic hinge. In torsion, it's even more bizarre in that if you twist such a closed wall tube, that all four walls will tend to go toward the centroidal axis here, and collapsing in will give this less and less stiffness in a torsional sense. And again, you get a torsional hinge, and this will wrap up just like taffy, especially with mild steel. So beware of trying to apply the Euler-Bernoulli theory too broadly, especially when you have thin-walled beams.